Hi class, in this video we want to continue our study in chapter 12 by moving into section 12.2 talking about vectors. Now for many of you who have taken a physics class before, this concept of vectors will be a review. So in this video what I just want to do is talk about vectors in general, and then I'll follow this up with some numerical examples in the classroom. Okay, so first off, the term vector is used by scientists to indicate a quantity such as displacement or velocity or force that has both magnitude and direction. Vector is often represented by an arrow or a directed line segment. Okay, so the length of the arrow represents the magnitude, and the arrow points in the direction of the vector. So we denote a vector by printing a letter in boldface. So whenever you see like a bolded V, this means vector V, or by putting an arrow above the letter. So you would see we'd have this vector V, and we know it's a vector because there's this arrow above it. So for instance, suppose a particle moves along a line segment A to B. So you have this particle that starts at A and it goes to B. The corresponding displacement vector V, shown in this figure here, is the initial point A, we call the tail, and the terminal point B, we call the tip. Okay, and we indicate this by writing vector V is equal to AB, and then you see the starting point and ending point, and this arrow above it tells me it's a vector. All right, now if you look at vector U, they kind of look almost the same, just it's a little bit moved. So notice that vector U, which we denote as CD, so it has initial point C and terminal point D, all right, has the same length and the same direction as V, even though it's in a different position. That's okay. In this case, we say that U and V are equivalent or equal, and we just write vector U is equal to vector V. Something called the zero vector, which we denoted as a bold 0, this has length 0, so it has no length at all. And it's the only vector with no specific direction. So it can't have a specific direction because it has no length dictating or indicating which way it's going or direction it's going. All right, so let's talk really quickly about combining vectors. It's actually pretty straightforward. So suppose a particle moves from A to B. So here's your particle. It goes A to B. So its displacement vector is that AB with the arrow above it. Then the particle changes direction. It hops from B to C. Okay, so once it's here, it goes whoop to C. All right, and it has a new displacement vector BC. The combined effect of these displacement is the particle has moved from A to C. So even though it took the long way to go whoop whoop here, we say the combined effort ended up being this pink arrow here. Okay, the resulting displacement vector AC is the sum of vectors AB and BC, and we write it as this AC here, this where we started and where we finally ended up, was you took vector AB and you added to it vector BC. All right, in general, if we start with vectors U and V, and we first move V so that its tail coincides with the tip of U, and define the sum of U and V as the following. So this is the definition of vector addition. If U and V are vectors, all right, vector position, so the initial point V is the terminal point of U, okay, then the sum U plus V is the vector from the initial point U to the terminal point V. Okay, so when you take a vector that goes like this, long as where one vector ends and where it ends, the next one immediately picks up, this new pink vector is the vector addition of the two. Okay, so the definition of vector addition is illustrated in this figure, and you can see why this definition is sometimes actually called the triangle law. All right, because you know your resulting picture here looks like a triangle. All right, in figure 4 here, all right, we start with the same vectors U and V, and as we did in figure 3, and draw another copy of V with the same initial point as U. Okay, so what you're seeing here is we're having V here, and on top of it we're putting U, and then U here, and we're having it V here. So what you're noticing, what's different here is where one vector ends, the other one picks up. That's not the case here. We have vectors that share an initial point, okay, but then shoot off in different directions. So completing the parallelogram here, all right, what we see is that this is the vector of summing them together. So this vector that shoots in the middle, this new U plus V vector, is the sum of vectors that where one's initial point is not the terminal point of another. All right, so this gives us also another way to construct the sum. If we place u and v so that they start at the same point, then uv lies along the diagonal of the parallelogram with uv as its side. So that's another way to visually represent the sum. All right, so let's do the following. Let's draw the sum of the vectors a, b shown in these figures here. Okay, so I want to show what the sum of this looks like. So first we move b and place its tail at the tip of a. Okay, so we're going to move b and place its tail at the tip of A, being careful to draw a copy of B so it's the same length and same direction. Okay, so you can see what's happening here. Okay, then we draw the vector AB starting at the initial point A and ending with the terminal point of copy B. And you can see this is the vector AB. However, if you do this differently, okay, you start, we could place B so it starts where A starts. Okay, so ending here like this. If we were to show the addition of these two vectors, you'd actually get the same exact thing. So even though you showed it as like this, that's the one vector. Here we showed them as going in different directions. The resulting sum vectors are still the same. Okay. All right, next, it's possible to multiply a vector by a real number c. In this context, we call the real number c as a scalar to distinguish it from a vector. So for instance, if we wanted to write 2v to be the same vector as v plus v, which has the same direction as v but is twice as long, in general, we multiply a vector by a scalar as following. It's pretty straightforward. If c is a scalar and v is a vector, then the scalar multiple cv is the vector whose length is c times, so in absolute value, times the length of the vector v and whose direction is the same as v, only if c is greater than 0, and it's the opposite if c is less than 0. If your scalar multiple here is equal to 0, then you end up just getting the 0 vector. All right, just a little bit of an illustration here of what it looks like when you multiply vectors by scalars. You know, here's the original vector v. Multiplying it by 2, it just doubled the length. Multiplying it by 1/2, it just shrunk it in half. Multiplying it by -1, it flips the vector in the opposite direction. Magnitude stays the same. And you can see the same type of deal with when you multiply it by -1.5. So we see that real numbers work like scaling factors here. That's why we call them scalars. All right, so notice that two non-zero vectors are parallel if they have a scalar multiple of one another. So in particular, the vector -v, which is equal to -1 times v, has the same length of b, but points in the opposite direction. So we call it the negative of v. So by the difference u minus v of the two vectors, we mean that if you have u minus v, it's the same thing as u plus -v here if we wanted to add that. All right, so we can construct u minus v by first drawing the negative of v, negative v, and then adding it to u by the parallelogram law as we saw in the previous figure. So alternatively, v plus u minus v is just going to be equal to u, and then the vector u minus v then when added to v gives u. So we can construct u minus v as we see in this figure here by means of the triangle law. All right, I'm going to follow this up with some numerical examples in the classroom next.